Welcome back to Physics 151 Online. We're starting a new section today which will occupy the rest of the semester, and that is the domain of thermal physics. And so we're actually going to be able to look at the fundamental constituents, the atoms and molecules of a substance, and ask how much energy they have. What kind of properties do they impart to the object? And what happens to two objects that come in contact with one another if their properties are different, specifically if they're at different temperatures. And so you can see the outline here is quite extensive, and it will take us through the end of the semester. So we'll begin today with a discussion of thermal energy, temperature, and heat. Now first we have to start with some definitions. And we understand through our everyday experience that we have numerous examples of hot objects and cold objects coming into contact. And we observe that the cold object gets hotter while the hot object gets colder. And if these two objects are left in contact long enough, then their properties will stop changing. And when that happens, those two objects are said to be in thermal equilibrium. And the property of the two objects that then is the same is something that we call the temperature. And we'll talk in just a minute a little bit more about what temperature means. It seems like it probably should be self-evident, but the so-called Zeroth law of thermodynamics states an important fact, and that is that if two objects are in thermal equilibrium, each with a third object, then they're in thermal equilibrium with one another. And so this principle allows us to define a temperature scales, because that third object could function like a thermometer. So in other words, if you had two buckets of water and an object such as a thermometer was in contact with the water in one bucket, and we left it there long enough so that their properties were the same, and then we take that thermometer and put it in the other bucket, and if its properties stay the same when it's in contact with that water, then we could say that those two buckets of water themselves are in thermal equilibrium with one another, even if they're not in contact. And so using that third object as a scale or as an indicator of the thermal energy that the system has is quite useful. Now, we have to distinguish between thermal energy and heat. Heat, in the way that we use it in physics, is always going to mean a transfer of thermal energy. So in other words, we could talk about one system having a certain amount of thermal energy. But if that system is brought into contact with another system, and then some of its thermal energy moves into the other system, that movement of thermal energy, that transfer of thermal energy, we refer to as heat. Now, thermal energy itself is really a reflection of the kinetic energy of the atoms and the molecules and the nuclei that make up that particular object or substance. And temperature, as we will see when we get into our discussion of the ideal gas law, temperature is a quantitative measure of that kinetic energy of the atoms and molecules. So we'll flesh that out in a little bit more detail coming up soon. But for now, in our focus on this kind of transfer of thermal energy, or heat, when heat is transferred, one of three things can happen. And the first is that the temperature of an object can change if it either releases thermal energy or absorbs thermal energy from another system. And so that would correspond to a change in temperature. Another thing that could happen, and if it does, it happens without a change of temperature, is that the phase of the object could change. So we could throw an ice cube at 0 degrees into a bucket of water, and so then the first thing that would happen if that water temperature is higher than 0 degrees is that thermal energy would flow from the hotter system, from the water, into the ice, and it would melt the ice and make it turn into liquid water. While that's happening, the temperature is not changing. So that phase change happens at 0 degrees. So that's another possibility. And a third possibility is that the object could do work on its surroundings, and it could thereby give up a certain amount of its thermal energy. So we're going to defer our discussion of that third process until we talk about ideal gases. And right now we'll concentrate on the first two. And these are the kinds of things that occur when objects at different initial temperatures are brought into thermal contact. And then there's a transfer of heat until they reach a common final temperature. And the study of these kinds of transfers of heat is called calorimetry. You may have done calorimetry problems before, and we'll do some in this course as well. So, in calorimetry, there's two important equations that we use to quantify the amount of heat or the amount of thermal energy that's transferred. And Q is the symbol that we use for this transfer of thermal energy. By convention, Q greater than 0 means that a system absorbs heat from something else. Q less than 0 means that the system releases thermal energy. And so when we have a change in the temperature of an object, then the heat transfer that is caused by that process is related to the change in temperature through a constant C that's called the heat capacity of that system whose temperature is changing. More often, though, rather than use the heat capacity, which is the amount of joules per kilogram that correspond to that system, we use something called the specific heat, because you'll notice that specific heat is really the heat capacity but divided by the mass of the system. And that's more useful. Rather than thinking of a system having a different amount of heat capacity depending on its size, it's more useful to think about something like copper having a certain value of specific heat no matter how large the piece of copper is. So this MC delta T is the expression that we'll most often use to talk about heat transfer when a system's temperature changes. But the other possibility, as we mentioned already, is that the transfer of heat results in a phase change of the object at a fixed temperature. So the Q for this kind of process is plus or minus the mass of the system times a constant L called the latent heat of transformation. And so you see unit-wise that L, if Q is an energy and it has units of joules, then L has units of joules per kilogram. And so L is something that we can quantify for a particular sample or substance. Water has a well-defined heat of vaporization, and as well as a heat of sublimation, or a heat of solidification, right? So depending depending on the kind of phase change that we have, we'll use the particular value for L that corresponds to that phase change. Notice, however, that the Q value, we have to put in a plus or a minus into this equation depending on whether the substance is absorbing or releasing heat. And I'll just give an example. I talked previously about an ice cube put into a hot bath of water, and from the perspective of the ice cube, it will be absorbing heat from the warmer water as it melts. And so for the ice cube, the Q would be positive M times L. In other cases, depending on the phase transformation that might be happening, that Q could be negative, and you have to think about this and put this into the equation in the proper way. In case 1 above, when there's a temperature change, as long as delta T is defined as T final minus T initial, the sign of the Q gets taken care of automatically, right? Because if a system goes from a higher to a lower temperature, then delta T is actually negative, and that means that the system releases heat. But when we have a phase change, we have to put that plus or minus in depending on whether the system absorbs or releases heat. And so the important master equation for the study of calorimetry is the following: that in an isolated system, if you have, let's say, two objects that come in contact with one another, but they are thermally isolated from the rest of the world, the sum of all of the thermal energy transfers, the sum of all the heat terms, must be 0 if energy is conserved. And as in an isolated system, energy must be conserved, and so in all kinds of calorimetry problems, the master equation that we use is this: we sum up all of the Q terms for all of the different components of the system and set them equal to 0. But of course it's important to pay attention to the signs. And I very much encourage you to use this equation exactly the way it's written, rather than trying to take one heat term and set it equal to another heat term. Simply add all of the heat terms together, and as long as the signs are done correctly, then they will equal zero. Because in an isolated system, some components will release heat, other components will absorb heat, and the sum of all of those positive and negative terms will add up to zero. So let's look at an example, a couple of examples here. And I won't work them out numerically here, but I will in class. So first, the simple case, 100 grams of water at 20 degrees C is poured from the tap into a well-insulated container. A 15-gram aluminum block, initially at 90 degrees C, is dropped into the water. What's the final state of the system? Okay, and the final state of the system means how much of each component, the water or the aluminum block, is left, and what temperatures are they at. And so, in this case, it's pretty simple. There won't be any changes in phase, because water boils at 100 C, right? And the aluminum block starts off below 100 C. So there's no way that this 100 grams of water could heat up all the way to 100 C. So what we know for sure is the water will heat up, the aluminum block will cool off, and together they will reach a final equilibrium temperature. So this, for the aluminum block and the water taken together as the system, and assuming that this system is insulated and so it's isolated from the rest of the universe, we just add up the heat terms, right? So we say that the Q of the aluminum plus the Q of the water equals 0, and the Q of the aluminum, right, is the mass of the aluminum times the specific heat of aluminum times the final temperature minus the initial aluminum temperature, right? And then for water, mass of water, specific heat of water, T final minus the initial temperature of the water. And the two T final terms are the same, right? Because if we wait long enough and the aluminum and the water end up in thermal equilibrium, they will be at a common final temperature. So this equation then, of course, the sum of those two terms is equal to 0, and all we need to do is solve for the final temperature, TF, paying attention, of course, to the units that are involved. So that's a simple calorimetry problem. One last step, as we always do in any kind of physics problems when we're done, is we check the units and we check the value. And here is a common sense test. We know, using the initial conditions given in the problem, that the final temperature of the system, when the water and the aluminum reach equilibrium, has to be somewhere between 20 degrees and 90 degrees, right? If it were less than 20 or greater than 90, we would know we did something wrong, and we would have to go back and check our work. So that's the final test. Now here's another situation that's a little bit more complicated. Let's assume that we have water and ice, 100 grams of water, 10 grams of ice, and they're initially at 0 degrees C. So they are in thermal equilibrium with one another, and the ice is not melting and the water is not solidifying because they're both at 0 degrees C. Into that mix, we put a 100-gram copper block that's initially at 90 C. So what's the final state of the system? This problem is a little bit more complicated because there's two different things that could happen, and we'll have to do the calculation to figure out which one is the correct one. First, all of the ice, there's only 10 grams of ice, so all of the ice, when the copper block is dropped in and it gives up some of its thermal energy to the water-ice mixture, all of the ice could melt and then turn into water, and therefore the resulting 110 grams of water could heat up to some final temperature that would, of course, be greater than 0. So if that's the case, what we need to do is find the final temperature of the water and copper system. So that's one thing that could happen. The other thing that could happen is perhaps maybe the copper block only provides enough thermal energy so that some of the ice melts, leaving the 100 grams of water and some of the ice still in the solid form. If that's the case and there's still some ice left when the system reaches thermal equilibrium, then the temperature will still be 0. Although the copper block, of course, will cool down all the way to 0. So if that's the case, the unknown that we need to find is how much of the ice melts. And so we really can't figure out which one of these happens just by reading the problem. We have to do some calculations and see which one makes sense. So I'll work out this example in class and give some hints on how to set this kind of problem up. So these are two simple types of calorimetry problems, and you will have some practice doing these kinds of problems in your homework. I'll see you in class.